Robin Singh and I am going to deliver a lecture on in-place printing of carbon nanotube transistors at low temperature. So this is the outline of the lecture, which includes introduction, printing technologies, inkjet versus aerosol jet printing, carbon nanotube thin film transistor device architecture, operations of thin film transistors, comparison of TFT technologies, in-place printing of carbon nanotube thin film transistors, and comparative study of relating properties of CNT TFT prepared by various printing methods. Thin film transistors are the most basic transistor type in printable and the flexible nanoelectronics. As its name implies, it is generally made up of those materials which are suitable for forming thin films on the different type of substrate, whether they are glass, silicon, paper. Thin film transistors are the type of field effect transistors, and their basic principle is to control the current flow between the source and the drain. The voltage applied across them give rise to an electric field in the semiconductor, which attract, accumulates, and transfer the charges. And these creates a channel for charges and let them move very easily between the source and the drain contacts. There are various semiconductor material which we can use in TFTs like the amorphous silicon, polycrystalline silicon, and the compound semiconductors. There are two types of 2D printing technologies. The first one is the non-contact and another one is the contact based. Non-contact based includes the inkjet and the aerosol jet printing. Contact based include screen printing. So this is the non-contact based. The inkjet printing and the aerosol jet printing. There are the major difference between inkjet and aerosol is the continuous streaming and non-continuous streaming. So there are three major differences why nowadays people use aerosol jet printing over the inkjet printing. The first one is the print resolution. Aerosol printing allows us to achieve a higher print resolution, almost 2 to 4 times higher than the inkjet printing. The resolution printing with the aerosol jet is around 10 microns, while using the typical inkjet printing is minimum resolution achieved is 20 to 25 microns. The second factor is the viscosity of the ink. The aerosol jet have used we can use a lot of amount of materials for the printing, while in the inkjet printing inkjet printing is used with a low viscosity. The third factor is the distance from the print head to the substrate. The aerosol jet has a greater opportunity to vary the distance between the print head to the substrate. It is possible to print on a non-flat substrate and also possible to create a 3D contacts that inkjet is practically impossible. So this is the video which shows how the aerosol jet printing is done. Basically, the aerosol jet process uses aerodynamic focusing to precisely and accurately deposit the electron into the substrate. The ink is placed into the atomizer, which create a dense mist of material droplets between 1 to 5 micron diameter. Then the virtual impactor, which removes the excess gas to create dense aerosol mist. Then this aerosol mist is then delivered to the deposition head, where it is focused by the sheet gas. which surrounds the aerosol as an annular ring and prevents any clogging. So we have carbon materials like graphene, carbon nanotube, carbon blank, carbon fiber, which can be used for inks in additive manufacturing and conventional printing techniques. And they have their beneficial properties and the potential uses. So why we use carbon nanotubes over the other materials for printing TFTs? Single-wall carbon nanotube thin film transistors have a network stick-like one-dimensional nanoparticles as the channel materials, so which increases basically probability of the conductivity, and the electrical performance significantly depends on the pre-location behavior of the network. The pre-location is basically defined as the minimum loading of the CNTs in the ink to establish a conductive network path in the channel from the source to drain when printed over the substrate. This is the basic CNT device architecture. The p-doped silicon substrate serves as a conductive backgate with the SiO2 as the gate dielectric. A CNT film prepared in which it is wrapped with a surfactant and dispersed in toluene, and, prepared ink is printed with a pneumatical atomized aerosol jet. This CNT pattern acts as a channel for the CNT TFTs. We also use silver nanowire contacts onto the channel. There are the various operations of the TFTs. The first is the following are the basically the parameters for the TFTs for consideration. First one is the drain current, and then threshold voltage, on and off current ratio, sub-threshold slope, contact resistance, capacitance, and the frequency response. Along with all these parameters, high field effect mobility also plays important role because it provides high cutoff frequency and high current pass through the CNT. So these are the basic terminology we use in the next slides. So W is here the width of the semiconductor layer that is covered by the source and the drain current. The gate length is L. So when we apply the small voltage between the drain and the source, the drain current varies linearly with the drain source voltages, and the channel has the characteristics of the resistors. So the how ID is calculated. It is calculated by the multiplication of drain conductance with the voltage applied across the source and the drain. Field effect mobility. It basically provides high cutoff frequencies and high current pass through the channel. Linear operation drain current. In the linear region of the transistor operation, when the VDS is lesser than VGS minus VT, then the ID current is calculated by the following expression. And when the VGS is far less than VGS minus VT, then it will simplified to the another expression. A saturation region drain current for a large drain to source voltage when the VDS is greater than VGS minus VT and VGS is also greater than VT. The transistor is biased in saturation region of the operation. The following expression is used to calculate the drain current. On and off current is also important parameter, and it is defined as a ratio of the on current to leakage current. Subthreshold slope. The subthreshold slope describes the turn-on characteristics of the device and is defined as the change in VGS required for a 1 decade change in the ID. in the region well above the threshold voltage, and it is calculated by the following expression. Ideality factor. Ideality factor N, which is calculated as the S multiplied by K into T ln of 10. Contact resistance. The active layers of the OTFT are generally highly insulated with a low intrinsic carrier concentration. For inorganic TFTs, a highly doped microcrystalline silicon layer is deposited on an active layer in the contact region prior to metallization to improve the carrier injection. The formation of efficient injecting contact requires a suitable match of the work function of the metal contact and the relevant conduction level of the organic semiconductor. The significant capacitance between the terminal of the OTFT are the gate source and the gate drain capacitance. The drain source capacitance is much smaller and can usually be ignored. The overlap length can be larger in OTFT, sometimes 10 micrometer or more. The reason for overlap is the fabrication processes used. Large performance gains then comes from the reducing the channel length. If the amount of overlap is fixed and can't be reduced, so the overlap capacitance could be dramatically reduced if the self-aligned OTFT process was to be developed. So what is the difference between the inorganic and the organic TFTs? Organic and the inorganic TFTs also differ in the way of source and the drain contact to active layers are formed. For inorganic materials such as silicon, the contacts are usually formed by the using highly doped contact areas on which some metal is deposited to form good ohmic contacts. The conventional doping of the organic semiconductor material is not feasible, so the metal is deposited directly on the undoped semiconductor. This will not produce a good ohmic contact, but instead of Schottky contact. So this is the comparison chart how the various TFT technologies used to make devices. We have the amorphous silicon TFT, metal oxide TFT, SAM organic TFT, and inkjet organic TFT. If you see the process temperature, then inkjet organic TFT works is fabricated at the room temperature, and it uses the inkjet printing technology. SAM organic TFT uses the shadow masking technology, while the metal oxide TFT uses roll-to-roll lithography. The feature size of the inkjetted organic TFT is 50 micrometer, while on the amorphous silicon TFT is 8 micrometer. The mobility is also an important factor. So the inkjet printing organic TFT has 0.01 mobility. In-place printing of the carbon nanotube transistor at very low temperature. So the in-place means that we don't have to remove the substrate for doing post-processing steps. So what are the steps in fabrication of in-place printing? The first one is the substrate cleaning, then the wafer functionalization, then the printed CNT channels, and in-place printing, and then it is followed by the silver nanowire ink and the printing. There is a short video which shows how the in-place printing works. So these are the comparative study for relating properties of the CNT TFT which were prepared by different printing methods. So in the reference one, which used the screen printing, and it used the top gate TFT architecture, and they used the contact material as silver, and they achieved the mobility of 7.7. If you see in the reference 5, they used the screen printing using the silver contact material and achieved the mobility 35.5. And when we use the aerosol jet printing using the double gate architecture, and they also use the contact material as silver, and they achieved the mobility around 3.2, and everything was in place. These are the references. Thank you.